Now that we've had a chance to look at the output from PCR, all of the plots, I want to take you just through one example where PCR seems like a really good idea. And this is a big data set. There's 120 numeric input variables, and they're just labeled V1 through V120. There's one numeric target variable labeled target, and then finally one variable that indicates the test set. So when test is 1, that's a test observation. When test is 0, it's a training observation. I won't give you the source of this data, it's a secret, but we will come back to it later in this semester. Now, the first thing we're going to do with this data is just implement OLS regression, ordinary least squares. For that, I'm using procreg. Now, because this is a large data set, it actually exceeds the size limits on our server. So I have to override that and tell it to use all the data observations. I'm only using the training observations. And I'm going to output the parameter estimates so that I can score the test data. The model target equals all of the variables. And you can also take a look at the variance inflation factors here if you would like. We're then gonna score the test data. So I'm using only the test observations. I'm inputting those parameter estimates that I outputted in the step above. And I'm gonna output all of that test data and the predictions to a data set called out. I'm gonna use that again later. But this out data set, if you examine it after running this, you'll see it contains all of the data plus all the test data plus the predictions. Now, we can look at some of those VIFs and they don't look so good. This is just the first, not even the first, it's first 27 rows and then rows 66 through 83 of the VIF table, just to pull out some to show you that they're really big. This is a problem here with this data set. So one of the solutions to that can be to use principal components. So the first thing we're going to do here is find the optimal number of components. I have to admit I didn't even run this because I know that it's going to choose 15 factors. 15 is the maximum factors that seems to be allowed by procPLS. You could actually push this a little bit farther if you'd like to try by using procprintcomp and putting those components into procreg. But for now, we're just going to see how we do with 15 factors. Again, all of the training observations go in here, and I'm going to have to use ODS output to get these parameter estimates. Now, if you're not familiar with the ODS commands, that's okay. They're a pain, honestly, but what they do is they allow you to take any table from the results window and output it to a data set. So here I'm putting the table called parameter estimates into an actual SAS table called PCR estimates. And I have to have this solution option to make that work, to get those parameter estimates, because the estimates I'll get will be for raw data, no standardization or factorization required. Now, finally, I want to score that test data with the PCR model I just created. To do this, I have to create a table of scoring estimates from that ODS output I just got. So this data, PCR estimates, if you just take a look at that and compare it to the output from procreg, you'll see that they're not the same, but they're very close. So these two procedures just transform the PCR estimates so that it matches the structure of the output from procreg, so that we can use it with procscore, which is what we do next. I'm actually putting the output from the first procscore, from the procreg work, into this procscore, because again, that contains all of the original data plus my OLS predicted values. So by using that, I'll have both predictions now on the same table, that final table being called out 2. So the final step would be to compare these two models. You can do that using R squared. I use proccore to just compute Pearson's correlation of each of my predicted values with the target. Now, this is just R. I would have to square it to get R squared, but I can see that the correlation is bigger for PCR, which means that PCR will win here. This second proc-sequel just computes the root mean squared error for each model. And again, it's lower for PCR. So there you have it, a situation where PCR beats OLS. And that's pretty cool. It's only got 15 variables versus 120 in OLS.